Today we're going to be talking about factoring binomials. So remember, binomial meaning two. That means there's two terms in the polynomial expression. And of course, even though we're going to go into special patterns today, please don't forget that there is just the plain old way of factoring out the greatest common factor. So if you're going to factor a binomial by factoring out the greatest common factor, what you need to do is identify the greatest common factor of each term and then factor out that greatest common factor. You'll know you did it correctly because what's left will not be further factorable. So for example, in 6x squared minus 3x, the greatest common factor is 3x. So if I do 6x squared divided by 3x, I'm left with 2x. 3x divided by 2x, I'm left with negative 1. And the only thing 2x and negative 1 have in common is 1. So since their remaining greatest common factor is 1, I know I did it correctly. Before we go too deep into special patterns today, go ahead and center yourself and try out these problems before we go through it formally. So pause your video, try them out, and then we'll compare together. So for this first one, their greatest common factor is a 4. And in particular, 4x divided by 4 is going to leave us with x. 8 divided by 4 will leave us with 2. And what we just did was we undid distribution. So if you were to redistribute it out, 4 times x is 4x, 4 times 2 is 8, and back to the original. For the second binomial, between 15y and 10, their greatest common factor would be 5. 15y divided by 5 gives us 3y. Negative 10 divided by 5 gives us minus 2. And indeed, if we were to expand it back out, we'd be back to the original. For the next one, their greatest common factor will be a 6a. If I take 12a squared divided by 6a, that's going to leave us with 2a. 18a divided by 6a leaves us with 3. And again, if I were to expand it back out, back to the original. For this next one, I might want to keep a little bit better careful track of each individual type of term. But for the coefficients, their greatest common factor is 3. For the constants, their greatest common factor is m. And then for the variable m, their greatest common factor is m. And for the variable n, their greatest common factor is n. So I'm going to go ahead and pull out a 3mn. And this one I'm actually going to formally write down visualizing what would be left. So I'm going to take each of those terms and divide it by a 3mn. So in particular, that first term is going to stay the same, 3mn. 6m squared n divided by 3mn. 6 divided by 3 leaves us with 2. M squared divided by m leaves us with m. N divided by n just stays as is. 3mn squared divided by 3mn. 3 divided by 3 is 1. M divided by m is 1. N squared divided by n leaves us with a minus 1 because that negative out front is going to stay there. And 2m and negative 1 have nothing else, negative 1n in common because n squared divided by n is a single n. So that would be all that's left is 2m minus 1n. Because again, those 3's cancel, m's cancel, but we have n squared divided by n is still an n. And again, if you were to re-expand it out, you would get back to the original. Last but not least, this final one, we would have a 7 in common between 21 and 14, and then an x squared in common between x cubed and x squared. And then 21x cubed divided by 7x squared will leave us with a 3x. 14x squared divided by 7x squared leaves us with minus 2, and that would be our final answer. And I'm just going to box in all of those. Now, the only other way you might be factoring a binomial is if it's a special pattern either of difference of squares or the sum or difference of cubes. So let's go through difference of squares first. Recall you may have noticed from when we were working forwards and multiplying polynomials that if I had something like a minus b times a plus b, a times a is a squared, a times b gets us plus ab, negative b times a gets us minus ab, and then negative b times b gets us negative b squared. And ab minus ab will cancel to make 0, and I'll be left with a squared minus b squared. And in general, this will help us factor the pattern if I have a binomial such that I can break down the first term as being a term squared minus another term being the term squared. In this particular example, x squared minus and then 9 is 3 squared. I can break it down into x minus that term, x plus that term that had been squared. So in this case, x minus 3a, x plus 3. And again, you're working backwards from the initial knowing how to FOIL out a minus b, a plus b becoming a squared minus b squared. So in order to do this, the first thing you really need to identify is what the heck is being squared. So for this first one, the first term is an x squared, but in the second term, 81 is the same thing as 9 squared, because 9 times 9 gets us 81. And now we can visualize that this will factor into x minus 9, x plus 9. And that becomes extra important whenever that leading coefficient is not 1, because in 16x squared minus 25, that really was 4x all being squared, since 4 times 4 gets us 16, minus a 5 squared. So that would break down into 4x minus 5, 4x plus 5. Again, that coming from what was really that first term, and then what was really that second term that was initially being squared. You need parentheses on both. So go ahead and try these next three yourself, and then unpause your video in order to compare. So for this first one, 49y squared is really 7y in parentheses squared minus 1 squared, since 1 times 1 gives us 1. So we would have one parenthesis that would be 7y minus 1, and the other one would be 7y plus 1. And again, if I were to FOIL it back out, I should get back to the original. For the next one, both of them we got to really carefully think through both a variable and a number that must have been squared. So 9 times 9 gives us 81, so it must be a 9, and then a squared times itself gets us a to the 4th, so it must have been 9a squared, all squared there. Similarly, 6 times 6 gives us 36, so there must be a 6 there, and b times b gets us b squared, so there must be a b there, so that must have been 6b all squared. Once I've then identified that, that tells me exactly what to use in my difference of squares. Because now I can visualize, oh, it must have been, let me change colors here, 9a squared minus 6b times 9a squared plus 6b. And I'm going to rewrite that a little bit neater, just so that anybody still looking at these notes can read that. And then you're done. So again, that key is to recognize what must have been initially squared. Same deal here. So that first term, 10 times 10 gives us 100, so 10 must have been squared. M times m gives us m squared, so it must have been an m. N times n gives us n squared, so that must have been an n, all being squared. Notice my usage of parentheses, minus 7 times 7 gives us 49, so that must have been a 7 squared. Now that I have identified that, I can recognize this is 10mn minus 7 times 10mn plus 7. Again, that key is to plus minus that last term, so that when you do a negative 7 times 7, for example, that gives you negative 7 squared, aka negative 49. The other key pattern that shows up sometimes is the difference of cubes. And for the difference of cubes, once you have identified what are the two terms being cubed, the order of the remaining numbers, terms is going to be the same. So it's always going to be an a and a b, either plus or minus in the first parenthesis. And then you're always going to have an a squared, an ab, and a b squared in the next parenthesis. So if you remember ab, a squared, ab, b squared, you're good to go. Now, how does the order of those remaining terms work? Well, for the first one, it's always the same sign. So if this is plus, then opposite sign. So if this is plus, this is minus, and then always positive. So the last one's always plus. Sort of similarly, I'm going to show this with the negative version. We always have AB, A squared, AB, B squared. It always follows SOAP, so it's going to be same sign, opposite sign, always positive in terms of those orders. Now, in order to recognize what's A and B, it might be worth actually explicitly noting. So, for example, in either x cubed plus 8 or x cubed minus 8, that must have been x cubed plus 2 cubed or x cubed minus 2 cubed, since 2 times 2 times 2 gives us 8. So in this formula, we recognize that means A in this case is x, b in this case is 2. So you would end up with, this case it would be a, b, a squared, ab, b squared. So in particular, that's always the x plus 2 in this case. X squared minus 2 times x is 2x. 2 squared is going to give us 2 squared. It will give us 4. And that's why you end up with the parentheses that you end up with. So let's practice that a little bit. And again, that key part will be initially identifying what has to be a and what has to be b. So in this first example of x cubed minus 27, that must have been x cubed minus 3 cubed, because 3 times 3 times 3 gives us 27. Then you're going to fill it into your formula. So it's always a and b, and then a squared, ab, b squared. 3 times 3 is 9. And then you're going to fill in your signs. So same sign, opposite sign, always positive sign. And this can seem a little bit magical, so let's go ahead and actually practice checking our work with this to make sure that we're doing that right. So I wanted to kind of prove to you that this does indeed work. So if I were to completely expand this out to check myself, x times x gets us x cubed, x times 3x gets us plus 3x squared, x times 9 gets us 9x, and then we'll want to keep on going, and I'm going to start vertically aligning my terms. Negative 3 times x squared gets us minus 3x squared. Negative 3 times 3x will give us minus 9x. Negative 3 times 9 gets us minus 27. And lo and behold, those middle terms do indeed cancel out, and you're just left with x cubed minus 27, which was our original. I would encourage you to go ahead and pause the video and prove to yourself that the positive version, so the sum of cubes formula, also works, maybe even with the same numbers, because it does. So let's go ahead and try the next one. So once you sort of have convinced yourself that the sum and difference of cubes formula work, again, it's a key of recognizing what's being cubed in each one. So for this first one, 27y cubed, it must have been that it was a 3y all cubed, since 3 times 3 times 3 is 27, y times y times y is going to give you that y cubed. Plus, and then 64 must have been 4 cubed, since 4 times 4 is 16, times another 4 is 64. And then we're going to start to fill that into our formula. So it's always going to be a, b, a squared in this case would be 9y squared, because 3 times 3 is 9, y times y is y squared. And then ab, well, we're doing 4 times 3y, so that'd be 12y. And then 4 squared, which would be 16. Now we're going to fill in our signs. So it's always going to be the same sign, opposite sign, always positive. Soap. And then that would be our final factored form. It cannot be factored further from there. Now let's go ahead and identify with the next one. So for the next one, you would have that the first term must have been a 5a all cubed, since 5 times 5 is 25, times yet another 5 will give you 125, minus a 1 cubed. And now you're going to want to fill that into your formula. So same deal. So you're going to always have a, b in that first parenthesis, and then a squared in this case. 5 times 5 is 25. A times a is a squared. So that'd be 25a squared. ab, which in this case would just be 5a, since 1 times 5 is just 1. 1 times 5 is just 5, so 1 times 5a is just 5a. And then last one, 1 squared is just 1. And now we're going to fill in our signs. So it's going to be same sign, opposite sign, always positive for your nice, beautiful final answer. For this next one, same exact deal. So I'm actually going to encourage you to go ahead and pause your video and try these next two yourself. So identifying what must have been initially cubed and then comparing. So for the first one, it must be the case that this is a 2mn all being cubed. And actually I'm going to write this where I have a little bit more room. So it must have been a 2mn all being cubed, since 2 cubed is 8, m cubed is m cubed, n cubed is n cubed, plus, and then for the next term, that would be 3 n all cubed. Now, I'm going to pause actually because you notice how these both have an n in common. I'm going to make my life easier if I actually factor out that n first and then do the difference of cubes on the remaining term. Had you not done that, you should notice that there's an n in all of your terms, and then you can go ahead and again factor that guy out first. So let's go ahead and actually fix that. So first I'm going to factor out the n cubed, and then I'll be left with 8m cubed plus 27. So really that's n cubed times, in this case, I'll go ahead and differentiate that color. That would be 2m all cubed plus 3 cubed, since 27 is 3 cubed. 8m cubed is really 2m in parentheses cubed. And now I can go ahead and use the same formula as I've been using. So there's still going to be an n cubed out front. And then I'm going to have a squared in this case is 4m squared. AB would end up becoming 6m, since 3 times 2m is 6m. B squared is 9, and then I'm going to fill in my signs. So it'll be the same sign, opposite sign, always positive. And then that gives us our beautiful factored final answer there at the end. The last one, same deal. So the first term is x cubed, and then 343 might not be something that you instantly recognize, but that is actually 7 cubed, which you could do from some educated guessing and checking. And in particular, if I do 49 times 7, 9 times 7 is going to get us 63. Write down the 3, carry the 6. 4 times 7 is 28, plus 6 is going to give us 34, so hence the 343. And then again, you want to fill it into your formula. So it's always going to be a squared, b squared, and then fill in your signs. So same sign, opposite sign, always positive, and then you are left with your beautiful final answer. Sum and difference of cubes is a little bit rarer to come across, but it does happen, and in particular you're going to recognize because you can write both terms as being something else cubed. But keep in mind you can still factor out a greatest common factor before you start doing that process. For difference of squares, if you have the same two terms, if you have the first term is something squared and the second term is something squared and they're being subtracted, you can write that as a difference of squares. Be careful that that does not apply for the sum of squares though. Sum of squares, there's nothing special. Absolutely nothing's going to happen. It's not going to be any pattern in particular. This particular one that I have written down, they actually are like terms, so I'm just going to go ahead and change that first term to, let's say, a y squared. So y squared plus 25x squared, there's nothing special going on there. It would have to be y squared minus 25x squared if it's going to have a special pattern, so be careful about that. The sum of squares is nothing special. It's still just prime. If it's the sum of cubes, though, that is not prime. That actually does have something special going on. So sum of squares, nothing special. Sum or difference of cubes, you're good. There is a special pattern. Difference of cubes, there's going to be a special pattern. And just no matter what, don't forget that you can still factor out a greatest common factor. And in fact, it's going to make even your special patterns be a little bit simpler if you factor out that greatest common factor first.